A differential equation together with an initial condition is called an initial value problem, often abbreviated as IVP. And our next example is one of these. So let's solve the initial value problem. dy dt equals minus t over y e to the t squared with initial condition y of 0 equals 1. So we'll solve the differential equation and then we'll put in the initial condition to find out what the arbitrary constant would have to be for this particular solution that goes through the point 0, 1 on the ty plane. I'm going to multiply both sides by dt, and I'm also going to multiply both sides by y. That will give me y dy equals minus t over e to the t squared dt, and then we integrate. On the left-hand side, I'll get 1/2 y squared. Remember, we're saving the c for the other side. On the other side, let's write this in more integration-friendly form. I'm going to rewrite the e to the t squared in the denominator as e to the minus t squared in the numerator. And now we'll need to do a u substitution. If I let u be minus t squared, then du would be minus 2t dt. Now I've got a minus sign out here, so I'm just going to put in a 1/2 du to replace the minus t dt. So I've got a minus and a t and a dt, and that's all going to get swallowed up into 1/2 du. So at this point I'll have 1/2. Remember, the minus sign got swallowed up into the du, and there's my du. And inside I have just e to the u. So integrating, at this point we'll have 1/2 y squared equals 1/2 e to the u plus c. Putting in what u really is, u is our name for minus t squared. And now we want to solve for y. So let's multiply both sides by 2 to get rid of those 1/2s. That'll give me y squared equals e to the minus t squared plus, and people usually just keep the c as a c, but I'm going to do that same thing I did in the other example to hopefully help the notes make more sense to you later. So c1 is just my name for 2c. And then to finish solving for y, we'll square root both sides. Don't forget you need a plus minus when you square root both sides of an equation. And under the square root, we'll have e to the minus t squared plus c1. And once again, the c1 has to stay inside the radical. We don't have a way of getting it out. By the way, although it's fine to leave your solution like this, just be aware that there's actually 2 solution functions described here. There's y equals the positive square root of e to the minus t squared plus c1, and y equals minus the square root of e to the minus t squared plus c1. Now we need to put in our initial condition. The initial condition, often abbreviated IC, was y of 0 equals 1. So that means I'm going to have 1 equals plus or minus the square root of e to the minus 0 squared plus c1. I'll square both sides to get rid of the square root, and that will also get rid of the plus minus. So at that point, we'll have 1 equals e to the 0 plus c1. E to the 0, of course, is 1. So c1, the constant inside the radical, must be a0. So our solution is, I'm going to make this a question. Is this our solution for this initial value problem? In other words, is this the solution curve that would go through 0, 1? Plus or minus e to the minus t squared. So is that what we want? Well, remember that this is actually two answers. And there's a problem with one of those. Do you see what it is? If I put in 1, 0 here, that's fine. I get a true equation because 1 equals 1. But if I put in the 1, 0 here, I get 1 equals minus 1. And that is not true, so that certainly cannot happen. So this is the one we want. I'm going to say no, our answer is not going to be y equals plus or minus the square root. That's the general solution, but for this particular solution, we have to have just the positive square root.